All right. Now we're going to do our review over some of the content pieces that you can be pretty sure are going to show up on the Physics C exams this year. So, last time we looked at general problem solving tips, things that sort of work in general. Today we're going to zoom in for sort of our last minute review of the most common things that are tested on the Physics C exams, either as a multiple choice or a free response. So these are the topics that might not show up as a question every year, but they're facts that are definitely worth knowing, and from my experience, they're tested very frequently, or at least enough for me to think about them when compiling this list. So we're going to start with tips that I think are good for both C tests. Then we're going to do 10 tips for mechanics and 20 for E&M. I could just think of more for that one, I guess. So, first tip, or the concept that shows up all the time, is functions. So anytime College Board can differentiate between the calculus and non-calculus physics courses, they will. And your sign that calculus is involved is seeing that there's a function. So if you're given f of t equals blah, you probably got to do some calculus for it. So in order to do that, you're really just sort of looking at, what do I want? Is it a derivative oriented thing or is it an integral? And you can figure that out by using the fact that the derivative is about a local rate of change. What is happening right now? Whereas the integral is about accumulating things. How much is there? What's happening between these two times? The only thing to be careful about is maybe an average rate of change that also takes place between two times. But usually when you have an interval, it means integral. Going on that same idea, we have density functions. So I would be very certain this is showing up on E&M in some way this year, but mechanics, they've also been really showing some love to the lambda functions. So a density function is basically telling you how densely packed something is, either a mass density or a charge density. And we have these different variants of it. So we have lambda, which is something per unit length. We have sigma, which is something per unit area, or we have rho, which is per unit volume. And then to actually integrate with these functions, lambda is pretty straightforward. Your density times size is just something per length times length. So usually you don't have to do anything strange there, unless if you have a circle. Then you have to use arc length, r d theta, for length, but that's very rare. Then we have sigma, or current density J for E&M. You have to multiply not just by dr, but it's by the d area element. So usually we have circular symmetry in these problems, which means that our area, or our change in area, is going to be 2 pi r, the size of a small ring, times its thickness dr. And similarly, if we go up a dimension, we'll look at spheres a lot for E&M, and the volume of a sphere, well, you can build it with these little spherical shells, 2 pi r, or sorry, 4 pi r squared with the area and dr for the thickness. Then for Newton's third law shows up on all the tests all the time, and it's really just saying anytime you have two objects interacting, the forces are equal, no matter what. No matter what, size, charge, current. If it is two objects interacting, you are guaranteed the forces are equal and opposite. So mechanics, they love this as like the planet and the satellite question, or like the moon's orbiting. They'll pick a big mass ratio and make you think that one of the forces is supposed to be bigger. Or they'll do it with Coulomb's law. They'll do an electron and something with 1,000 electron charge. The forces are always equal and opposite between objects. They also will try to really trick you by putting an electron near a wire that's moving. You'd think, oh, it's a tiny electron, the wire has to win out. No, equal and opposite forces. The thing that's not the same is acceleration. Then going back, we got Newton's second law. This one is big across all physics courses, and it's how you solve for velocity as a function of time usually. So of course, if you just know what the acceleration is, which is something you have to solve for a lot, you just find the net force and divide by mass to get acceleration. But occasionally, you're going to want to solve using a differential equation. So I always write the second law as the forces helping minus the forces resisting. You can set that equal to ma. And if you're getting points for differential equations, you can actually just set the force equal to m times the derivative of velocity with respect to time, dv dt. You do get a point on most of these Newton's second law diff EQs just for writing it in the form F net equals m dv dt. So make sure you write that derivative to make it a differential equation. So to solve differential equations, I know this is something my students always struggle with, and it seems to be carrying over from calculus as well, because we have some of the nasty ones with logarithms in it. But to solve a differential equation on AP Physics C, first, set up your equation using the physical law. If it's mechanics, it's probably Newton's second law, and if it's E&M, it's could be Newton's second law again if it's a like railgun question, or it could be a Kirchhoff's voltage rule, where its voltage drops around the circuit and you're solving for one of those quantities. So to do that, write your expression and then separate your variables. So usually this involves dividing the entire side, dividing the equation entirely by one of the sides so you have one left over. So you'll usually get something like dv over blah, 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 blah is equal to just dt. So that counts as separating. So basically getting dt by itself is a good strategy for these because we don't do a lot of time-dependent diff EQs. It's a lot of diff EQs that depend on the quantity itself. Like di dt equals something times I, or dv dt equals something times v plus constant. So you can always just separate it that way. Then you get a second point for integrating with limits, meaning like, do I know where the thing started, VO? Do I know where the thing ended, V of t? And t always goes from 0 to t. Or you could just say, yeah, I'm not doing a definite integral. You could just find the antiderivative of both sides and then attach a plus c integration constant, and that works too. And then you probably got to simplify it to get that third point. But the actual algebra is only one. So please separate, absolutely do the separation. That will get you a point. And then even if it's wrong, attempting to integrate with correct limits will get you a point too. Circular motion, this shows up in both courses. If you see something moving in a circle, your brain should automatically think mv squared over r. That is the governing equation for circular motion. So if an object is moving in a circle, then we can describe the force as centripetal. So it's important that centripetal is not a thing, like it's not a type of force. It's sort of an adjective that describes what a force could be doing. So in E&M, which we'll get to later, it's a magnetic force that's causing a centripetal force. So the magnetic force has the property of being centripetal. So if you're problem solving, you should just know that you can set ma equal to mv squared over r. So whatever is causing the acceleration, set that equal to mv squared over r, whether it be the Coulomb force, the magnetic force, tension, etc. And this means part of velocity is always going to be around the circle, and acceleration, a part of it's always going to be towards the center. I say a part of it because in mechanics especially, you might not get that pure circular motion uniformly if it's, for example, a loop-de-loop question, where you'll have gravity slowing you down as you climb the loop, but you still have a centripetal component. Another thing that really trips people up is the sign of work. So for the sign of work, the work done by an external force just tells you how much energy was added or removed from the system. And if this confuses you to think about, please draw a bar chart. So if I have a box that's just sitting on the ground, it has no energy. But if I push it, it now has kinetic energy. So I did positive work on the box from outside forces. Now it gets more complicated when you're looking at gravitational potential from orbits or electrostatic forces and potential energy, but this approach of just drawing a bar chart will definitely work. So for internal forces, you won't get this sort of idea, because with internal forces, the work is just going to be the negative change in potential, because the potential gets converted to kinetic, and the bars sort of like swap, where one bar goes up, one bar goes down. Now for your free bodies, only label the actual forces. So don't draw components, especially if you're given a ramp. Just draw the actual mg down force. Don't draw forces tip to tail on your diagrams. No credit for that. And if you're given a grid, it means that that is part of the scoring guideline, is something with the grid. So are the forces supposed to balance? Is the right force bigger than the left force? Is the second crate heavier than the first crate? Things like that. So you have to make sure that you are using the tick lines to respect whatever relationship is going on there. A general problem-solving tip, and this is a concept that shows up all the time, is some complex question that sort of baits you into doing it a way that's not energy. But please use energy whenever you can. Energy is the most utilized tool I think we have, especially for mechanics. You can use it for kinematics, right? The kinematics equation, VF squared is VO squared plus 2AD. That's a restatement of energy. Atwood machines, you can use energy for that. Orbits, right? We have this new form of gravitational potential, the negative GMM over R formulation of that. And then for E&M, anytime you want velocity in E&M, you probably need to use kinetic energy. You could also have to do some Newton's second law differential equation with the conducting bar, but I think that's pretty clearly not energy. And then lastly, you have that nasty LC circuit that people forget is actually an E&M of the oscillating circuit. And it's really just a capacitor and inductor trading energy. So you can use energy conservation for that too. And more on conservation laws, think about the ways that you can represent them. So I'm sure that you'll have some sort of representation to analyze, either on the multiple choice or the free response, that you have to showcase conservation of momentum or energy. And in E&M, that energy conservation shows up as Kirchhoff's voltage rule. So how are you showing that on a bar chart? Are all the resistor voltages adding to the battery voltage? Is the potential drop around a closed loop truly equal to 0? Is the momentum of the two crate system staying constant? And then for your graphs, same thing. It's usually showing that if K goes up, U goes down. So you have to show that sum is a constant. Now for mechanics, these are more just sort of random things I've noticed that are common questions. There's usually exactly one relative velocity question. So this is asking, if one person is doing this, they'll measure this speed. What does someone else measure? So if they're moving together or exactly against each other, so they're both moving horizontally, for example, one person will feel the velocity boosted, so it'll just be a pure addition. But the other variant of this is if they're moving perpendicularly, they'll actually measure a velocity component that adds via Pythagoras. So be on the lookout if it's going to just be a sum or if it's going to be added like vectors. For kinematics, common pitfall is trying to do kinematics when they don't apply. Kinematics only works with uniformly accelerated motion where A is a constant. So it does work with things like projectiles or constant force or Atwood machines, but it definitely doesn't work for simple harmonic motion or gravitation. So it only works if you have a constant acceleration. And if not, you might feel stuck, but don't worry. Energy is there. Like we said, energy is the best way to do this. And I don't even cover the kinematics equations in the E&M half of the course, so we're always using energy there. Energy is always the way. Now for some diff-EQ setups. So in mechanics, here's my formulation of it again. It's this helping forces minus resisting forces is my net force, and I can set that equal to m dv dt. Do not forget to write acceleration as dv dt. I know we've said this already, but it will get you a point, even if you have complete garbage as your net force. Write dv dt, attempt to separate, attempt to integrate, farm those points. And then if mass is changing, which if we get a dm dt, it is quite frankly over for everyone. You get something called a rocket equation, where you have this sort of thrust force that's changing your mass. So think about a rocket ejecting fuel or like a jetpack. So you get this equation where your F net is sort of this thrust change in momentum force. And you can separate that and actually solve for mass. And you get some logarithm relationship that we call the rocket equation. But I would really not expect to see that. That would be incredibly mean. When using forces, use the system approach. So if you have an Atwood machine where it's a block connected to another block on a ramp connected to a pulley, use the whole system first and then zoom in on whatever you need. So first find A. The acceleration is global. So if you find the acceleration first, you can solve for any tension force you need, for example, or a height change. So acceleration is always the key. And if everybody has the same acceleration in these problems, which they will because there's no slipping, that's going to guarantee that we can just use this system approach where I find only the external forces, which are usually gravity or parts of gravity if it's on a ramp. So like maybe an mg sine theta. So the mg's and the frictions are going to be your external forces usually, or maybe someone's pulling from the outside as well. And that's equal to your total mass times your acceleration, so solve for A. And a trick that people don't know about very often, so people definitely know about the first one, but people also don't realize that you can use this trick for the rotation version of the Atwood. It just turns out that your pulley adds an effective mass of beta times m, where beta is that moment of inertia shape constant. So for example, most pulleys are 1/2 mr squared, which means that your pulley would add a 1/2 m to your denominator with your mass. So that's a really quick shortcut. That saves you a lot of time, actually. This fact that the beta m gets added in rotation problems. That'll save you so much time. In terms of systems, be careful what your system is. This is more of a multiple choice thing. I'm really not a fan of the nitpicking the system questions, but be very careful to see what is and isn't allowed to be used. If the Earth is not in your system, there is no such thing as gravitational potential energy. That would all be external work in that case. So also get away from the phrase like something has potential energy, which is more of a middle school way of talking about it. Instead, it's the blank blank system has potential energy, right? Potential energy is due to forces and interactions, so it's two objects. Also, collisions. Be very careful about what is and isn't conserved. Linear momentum, P, is conserved if there's no pivot force or rotation around some sort of axle. So this is like that sort of rod that swings after a ball hits it. That would not be conserving linear momentum. But basically any just raw linear collision does. So two crates hitting each other, two cars, or anything like that. That's when momentum should be conserved just with linear. Angular momentum is conserved more often. And you'd be hard pressed to kind of find some of the collisions where angular isn't conserved, but it's only really helpful in that like swinging rod variant. Kinetic energy is absolutely not conserved. Unless if you have a magic elastic collision, kinetic energy is absolutely not conserved. Do not solve the bullet firing into the block problem by setting kinetic energy equal to potential energy at the very start and very end. You cannot conserve kinetic energy during a collision. Almost all of it can be lost. Or all of it could be lost, but in the ballistic pendulum case, you're going to lose a ton of energy firing that bullet into the block. So now we can talk about rotational inertia. So for objects of the same mass and radius, rotational inertia depends on how the mass is distributed. So objects with mass farther away have more inertia, so are difficult to accelerate. This is our classic like shape race. So a hoop will always lose a race down an incline to a disc because a hoop has to dedicate more of its energy budget into rotational kinetic. This would be the same reason why if you're racing them up a ramp and give them the same starting speed, the hoop actually gets to go higher because for the same speed, it would actually have more total energy. On the concept of torque, choosing a pivot is really important, especially in those like leaning ladder or static equilibrium questions. So when you're choosing a pivot point, think about what forces are acting on my object that I absolutely do not care about and are a pain right now. If you can find that location, that should be your pivot. Because whatever point you pivot around, all of the torques are automatically zero because there's no lever arm. If torque is R cross F and you have no R, then there's zero torque. So most commonly, this is used to eliminate that annoying like hinge force or the wall force on those static beam questions. But this is also a really clever way to solve for a rolling object on an incline, or also that toilet paper unrolling lab where you have someone holding and there's a tension force. You just say, I don't care about the tension force, so I'm going to make my torque about that point. But you do have to adjust moment of inertia when you shift your axis, which goes into the parallel axis theorem. This is common as a multiple choice, and you know it's parallel axis theorem if you see something about rotational inertia, then you move your pivot, and it's something about rotational inertia again. So if you're ever shifting your pivot location, you're using parallel axis theorem. So this is actually how you solve a lot of problems more efficiently, is if you can find that correct axis to pivot around that kills some of the torques that were going to be annoying for you otherwise. But just remember to shift your pivot using the parallel axis theorem. So you can pick whatever point you want. If you have if you have a disc rolling down a ramp and you want to pick the contact point to torque around, great. Just remember the moment of inertia is not the center of mass one in that case. You have to add that md squared. Last, there's not a whole lot of like equations to memorize / derive for mechanics. There's a lot more in E&M, which you'll see, which is mainly the reason E&M has like double the facts. But Kepler's third law usually shows up. I wouldn't be surprised if we don't see it at all, especially with the lack of gravitation in recent years. But Kepler's third law relates the period t of an orbit to the cube of the orbital distance. This does work for ellipses also. But we can derive this from circular motion. You just set gmm over r squared equal to mv squared over r, and you can get this relationship out. This is a classic derivation that I think it's a good review. It's actually one of my favorite mechanics derivations. Now for E&M. First up, we got polarization. So a neutral object is always attracted to charged objects. You might have learned in elementary that positives and negatives attract and positives repel. Well, it turns out that positives and negatives both attract neutral because the charge carriers are going to be either attracted or repelled and create a net attractive force no matter what. So if the neutral object is just isolated, you can't change its charge, so it's going to be neutral. But if you ground that object, it can pull charges out of the ground or send charges into the ground, so you actually can get it having a net charge. And there's that whole, like, when do I snip the wire thing, and that can determine whether it's positive or negative or zero net charge. And also, if the charge rod is far, far away from the sphere, like that type question, there's no polarization. Field and potential. People mix these up a lot. Electric field is the way that a positive charge would like to go, meaning positives are sources, negatives are sinks. The electric potential is a scalar that represents height. They're not the same. One is a vector that's about force, one is a scalar that's about height, but they are related. E actually points downhill, so the electric field points towards a lower potential. So in a conductor, the electric field is zero, because if the electric field wasn't zero, the charges would still move around to make it zero. And if the electric field is zero, that means that the slope of my terrain is zero, which means that I'm not changing elevation anywhere in a conductor. So conductors have zero E field, but not zero potential. It's just constant potential. So this is used to solve those like connected spheres question. So if you have any conductors connected, they got to have the same potential. To integrate for E field, you'll know it's not a Gauss's law question, but instead an integral question of k dq over r squared r hat if you're given a finite line, either on the end of the line or above it, an arc of charge, or a ring of charge. Since E is a vector, you might have to attach a sine or cosine to your integral and do some substituting. But if you find that a bit annoying, a pro tip for this is actually finding V first, because you don't have any vector stuff to deal with V, and then just take a derivative of V, because E is dv dx. All right, now for flux. So for flux, we define that as the amount of field that's piercing an area. And to do that, we find the field part that's actually perpendicular to the surface, or we call that the penetrating component. And once you have that penetrating component, you just multiply that by the area. So this will usually involve trig if your surface is angled relative to your field, but it is very simple. You just multiply by sine or cosine. So to do that, just draw your vector out of the surface and determine, do I want the adjacent or opposite side that's actually piercing it? And that tells you what factor to use. Additionally, this is seen almost every year on the multiple choice, is some question about Gauss's law and flux. So if you are talking about the word flux, then you should use the fact that Gauss's law says that flux is proportional to the enclosed charge, and that's it. So a common question says something like, I have a charge inside of a sphere. What happens to the flux if I double the sphere size? It stays the same, because you have the same charge in there. So will that question show up? Maybe not, but I feel like it shows up quite frequently, and people get it wrong every time. They feel like, oh, the sphere got bigger. The flux will obviously change because the field is less. But actually, the field decreased by a 1 over r squared, but the area increased by r squared, so it actually totally cancels out. So flux only depends on enclosed charge, not where it is, not the size of the surface, just the enclosed charge. So using Gauss's law, great quote here from Griffith's E&M book. Gauss's law is always true, but it is only useful if there is symmetry. Only try to use Gauss's law if you see a case that looks similar to one of these. Point charge / sphere. Then your flux works out to E times 4 pi r squared. E times sphere area. Above a line of charge, not collinear with it, you're not going to find a nice surface that gets pierced. But if you're above a long line of charge, a nice cylinder gets pierced 2 pi RL by the E field. And then if you're above a large plane, this is that weird, like, gotta memorize it sort of derivation, where you draw this sort of half above, half below surface. So you have two caps of area A that get pierced. So you have 2 EA of flux. Kirchhoff's rules. Don't forget that these exist. I know you won't, because you're going to use Kirchhoff's loop rule to derive a differential equation. But even in your most simple circuits, realize that Kirchhoff's loop rule and Kirchhoff's junction rule always work. So if you're stuck because you have a complicated circuit, or you feel like you don't know where to go next, see if you can apply a Kirchhoff rule. Can you find a missing voltage? Can you find a missing current? And if worst comes to worst, you can just set up a whole nasty linear system and solve it, because Kirchhoff's rules allow you to brute force it that way. And the loop equation is the basis for any sort of differential equation with capacitors, inductors, or both. Series and parallel. Two things in parallel series have the same current, right? Because there's only one path between two series elements, so they have to have the same current. And since current is charge per second, capacitors in series would have the same charge, unless if it's two connected directly together and nothing else, which we'll talk about shortly. Additionally, any two elements in parallel have the same voltage drop because they form a closed loop, and by Kirchhoff's loop rule, you know that if they make a loop with each other, they have to have the same potential. So a tricky case of this is that two capacitors connected to each other and nothing else, even though it looks like series, it's actually parallel, because the more fundamental rule is that they have to have the same voltage drop. So for capacitors in parallel, their Q over C's have to be the same. For power, know all three power formulas. So the one on the sheet is I delta V, but by doing an Ohm's law substitution, you can get the other two. And be on the lookout for total energy dissipated instead of just power, because if power is the rate that energy is used, an integral gives you the total energy. This is guaranteed to show up in some way. Short and long time analysis of circuits. So this does not require calculus. So if you see, like, after a long time, do not create a differential equation. Do not get that involved. It's easy. Short and long time cases are easy. So capacitors, at short times, there's no potential difference across it due to its no charge. So all current would freely flow. But then after a long time, it's fully charged. It doesn't want charge to move anymore. So it's a gap. So you either draw a wire at short times or a gap / hole at long times. And inductors oppose change in current. So inductors do the opposite. So if you start to send current through an inductor at time t equals 0, I always say that the inductor sort of wags its finger and says, oh, hell no, and does not let you to pass current through it. So inductor and capacitor behave opposite at short and long times. And afterwards, after you've let the current go for a while, and the inductor has successfully reduced the current change rate, it's going to be some non-zero constant value, so the inductor does not care anymore, because the current isn't changing, so it's a wire at long times. TLDR on that, just redraw the circuit with whatever thing the inductor or capacitor became. If you don't redraw the circuit, you're definitely likely to miss out on like a parallel versus series thing. So please redraw the circuit when that happens. For your loop equations, this is one of the two possible diff-EQs you could make in E&M reasonably. First, you could say that it's not Newton's second law. So hopefully you can figure out if it's a Newton's second law question or a Kirchhoff's loop rule question. But you should start from stating the loop rule, like literally write the loop rule. And it says it in the question sometimes, starting from Kirchhoff's loop rule. So you better write the loop rule. Then replace your delta V's with the relevant circuit quantity. So delta V across a resistor is IR, delta V's across a capacitor is Q over C, and inductor L d I dt. And of course, there's sign issues in there that you have to deal with. But then, to make sure it counts as a differential equation, you better have a derivative in there. So the inductor one, that's done for you. I and di dt show up together. But for a capacitor, you probably got to replace I with either positive or negative dq dt. And on that note, there are some parent functions to memorize to save you all this garbage algebra simplifying of the diff-EQ. So I call it the exponential approach, which is a constant times 1 minus e to the minus t over tau. So that's our graph that sort of ramps up to some constant value. So maybe your capacitor's charging to 12 volts, so it asymptotes to 12 volts. An exponential decay, so maybe it starts at 12 volts and goes down. The only circuit graph that doesn't look like this with inductors or capacitors is if you combine inductors and capacitors, and then you get that LC circuit that it unfortunately might be over for us if that shows up on the free response. But that's the one that oscillates as a sinusoid. Then for the mass spectrometer, this is just a reminder that charged particles in a magnetic field form circular paths. So the QVB magnetic force is causing a centripetal mv squared over r force. Other facts about the magnetic force: since it's perpendicular to velocity, it does no work, and thus cannot change the speed or kinetic energy of a particle. But acceleration and velocity are both changing because those are the vectors. So those vectors sort of sweep out a circle as they go around the circle. So those would not be constant, but the speed is, and the magnitude of the acceleration is, and the magnitude of the velocity is. The Hall effect shows up when you have a conductor in a B field just carrying current. You'll get positives and negatives will slightly migrate towards the opposite ends of the conductor that's carrying current. So you can probe it and get a really small voltage and use that to calculate drift velocity, for example. One thing that people get tripped up about is that current doesn't mean that its positive charge is flowing that way. It means that's the way a positive charge would flow. So in reality, it's usually the negatives that are carrying our charge. So you should do the QV cross B with the motion of negative charges, which should be against the current for the Hall effect. And that will affect the sign of your voltage. It'll tell you whether the relative polarity. That's actually one way we have evidence that it is the electrons that are moving and not the protons. All right, wires and magnetism. So wires, the B field around a wire circulates via the right-hand rule, where your thumb is the current and your fingers wrap around the field lines. So again, that's your right-hand rule. This is really easy to derive from Ampere's law, that B from a wire is mu naught I over 2 pi r. This is number one on my list of like equations to memorize that aren't on the sheet. It's mu naught I over 2 pi r from a wire. It shows up so often. And similar to that, the magnetic force being equal to BIL, or IL cross B, but that never shows up. I always just call this the Bill force. If you have a current carrying wire in a B field, it experiences a force given by BIL. And I rearrange the order just because I like to pronounce it like the name Bill. But substituting that in for B actually gives you another formula that I think is worth committing to memory. which is the formula between wires, the force between wires. So we have what we've been calling evil Coulomb's law, where it looks like this Coulomb's law thing with two wire currents on top, but it's not an R squared on bottom like Coulomb's law, it's R because it's magnetic field. And my class has called this the zesty ah wires theorem because wires that carry the same current attract. So it's not opposites attract, it's likes attract. Then for integrating for B fields, this is also on my short list of topics that I do not want to see, is the Biot-Savart law. Luckily, there's like two things that Biot-Savart could be used for. It's either that partial loop of currents, and actually a loop of current works out to mu naught I over 2R, so that loop actually, it just looks like the wire formula, except without a pi in it. Or a finite wire also uses that. But if you are going to use Biot-Savart, do not use the formula sheet version of it. Use this simplified version, where we're always just taking that sine theta. That just evaluates the cross product. Then for Ampere's law, with double capitals, I guess. Ampere's law is always true, but only occasionally helpful, just like Gauss's law. Only try Ampere's law for these cases. If it is a long wire or a cable, use a circle that makes the circulation work out to a B field spinning for a distance of 2 pi r. But if it's a solenoid or a slab, do that rectangle that sort of lives on the midline and then goes outside. Because then you'd have the magnetic field B circulating only for a distance x, because all the other wire segments cancel. More on solenoids. This is given to you in the sheet, the solenoid B field. It's just written in terms of little n instead of turns per length, so I wrote that out. Knowing the ampere derivation for a solenoid is important. It shows up quite frequently, and it's quite odd. It's not something that you would get figuring out live if you didn't remember how to do it. Because it's that weird partially in, partially out path. Some features of the solenoid field. It's constant. We assume that B is constant inside a solenoid, and it just instantly drops to 0. And to increase your solenoid field, you got to pump more current into it, or increase the turns per length somehow. Now for a couple inductions. Lenz's law. Changing the magnetic flux through a loop will generate an EMF via Faraday's law. And that EMF will generate a current to oppose the flux change. So figure out what way the flux is changing, and use that to figure out what you need to oppose it. So if I'm getting more magnetic field out of the page, I need a current that's going to wrap clockwise to go into the page. So if you find the way that B is changing, your your induced current will oppose that. So it either is fighting an increase in magnetic field, or it's reinforcing a magnetic field that's decreasing. Then for a special case of Faraday's law that I've actually been seeing more often, of all the Faraday's law free responses, almost all of them actually take this motional EMF idea, where if you're moving a conducting loop in a way that's changing its flux, you get an EMF induced. And the d phi dt works out to the magnetic field B times the rate that area is changing, and that simplifies to VBL. So my class calls this the VBL-Drizzy formula. This is also something that is worth knowing. This is probably number 2 on that list of like equations to know that aren't on the sheet. It's the motional EMF formula VBL. It doesn't apply often, but there's a whole genre of problems where it's relevant. And that's really your like railgun adjacent problems. And more on the railgun problem is this idea of resistive forces. So because of Lenz's law, we know that the magnetic field, or we know that the flux change is going to be resisted. So as an object moves through a B field and changes its flux, that magnetic force is actually going to attempt to pull it or push it backwards to resist that flux change. So there's some variants of this that allow you to set up a differential equation. So if you're just launching a bar and there's nothing helping it, then the Bill force just causes your acceleration, which is a slowdown. If you're just dropping a conducting bar into that magnetic field region, mg is trying to push it down, but Bill is trying to resist and pull it up. Or if you're going down a ramp, it looks similar, except you just tack on a sine theta, because it's not all of mg pulling it down the field, it's just the mg sine theta part. and that should say dvdt over there. And then to actually solve a differential equation, because you won't know what I is, you have to substitute I is VBL drizzy over R. And then you get some differential equation that usually works out to like V of t is V0 e to the negative b squared L squared over mr all times t. Something along that lines. So in terms of your differential equations, I am almost confident that you'll have a differential equation to solve in the free response. It is either a Newton's second law with Bill forces, or it's going to be some sort of inductor capacitor loop equation, or both. I've seen both as well. But realize that differential equations are a big part of this course because it's AP Physics C, and we want to show that calculus when we can. All right. Hopefully, we gain something out of this. Some last minute tips and some facts that show up a lot. Of course, these are things we should have done throughout the year, but it just kind of helps to have them in one place. So hopefully, this allows us some success. And of course, as usual, we'll see just how correct I am or incorrect I am when the free response come out after taking the test. So we'll see later. Okay.